Okay, so we will start the second day of this conference with Simon EKHAMMAR, sorry.
EKHAMMAR.
EKHAMMAR,
Very
okay.
good.
That will discuss about Q function, functional separation of variable, and boundary. So you have 35.
All right, wonderful. Thank you so much. So yeah, let me just start by thanking the organizers for putting together this great conference. And it's a pleasure to be here. And it's a pleasure and a bit of a challenge to talk about SOV. So I think this is the first time I will talk about SOV. So I think it's going to be a lot of fun. So I won't only mention SOV, but I also talk a bit about Q functions in general, then SOV, and also some connection with boundaries. So the part about boundaries is based on some paper together with Nikolai Gromov and with Paul Ryan. So Paul is in the audience, and I kind of view this talk as a prelude to Paul's talk. So I'll do the absolute most basic things, and I'll leave the advanced applications for Paul. And hopefully this will serve as a fantastic introduction. Of course, we were both part of doing the advanced part for the paper, just not to discredit myself. All right, so there is, of course, many different reasons to study Q functions and to study SOV. And I think everyone in this room has slightly different motivation. So let me just start by telling you what is my personal motivation for looking at these objects, which I know also aligns with some of you here, but not with everybody, I would suppose. So to me, the way I was raised into academia is that we do this to study n equals to 4 super young males. So it is a quite fantastic fact that there is integrability in the ADS-CFT correspondence. So let me just highlight where the formalism of Q functions and so on is most explicit. So what happens here is that we have a supersymmetric field theory. What is novel in this setting is basically that we have a coupling constant, G, and we have integrability where we can tune this coupling constant from very weak coupling to very strong coupling. This means that we have integrability both in what's known as a spin chain regime, but also in a string theory regime. And what we usually like to do in this context is to compute a spectrum, which is this little guy here, where we compute the 2-point function. And the way that I personally go about doing this is through a tool that is known as the quantum spectral curve. So the quantum spectral curve is the place where the Q functions make their appearance. So here is a very brief outline of how the QSE came to be. And it also kind of explains why spin chains plays an important role. So the start of the development of kind of integrability in the context of n equals to 4 is in some seminal work by Minahan and Sarembo, and even earlier in the context of QCD. So in the beginning, there was a spin chain and a rational PSU 2,2/4 spin chain. And then eventually, the coupling constant was turned on through various techniques, eventually leading up to this QSE. So what happens in n equals to 4, which makes it different from your typical rational spin chain, is that your Q functions have different analytic properties, so they have cuts. So usually when we work with Q functions, we like them to be polynomial, but potentially have some poles in some worst case scenario. But here they will be actually complex functions, and the task at hand is to really try to understand this complex structure. So I won't actually talk about n equals to 4 now. I will talk about rational spin chains. So why do I talk about rational spin chains and ADS-CFT in the same language? It's because when I take this coupling constant to 0, I do find a rational spin chain. And so if I can understand the rational spin chain, I would understand a very good starting point for understanding problems in supersymmetric field theories. So just to highlight the things that we do instead of computing spin chains. So in ADS-CFT, we study things like strong coupling, so quantization of string theory. Or we can study double kind of regimes of the ADS-CFT correspondence. So this here would be in some BFKL regime, which is an analytic continuation in spin. And so recently we tried to do this, and then you find some new novel spin chains that are different from the types that we usually see. So if you're interested in trying to figure out what spin chain this is, I will be very, very happy. So that's why I'm trying to promote it. So the point here is that I just wrote down the beta equations. And as all of you are well aware, beta equations have a tendency of looking awful at some point. So let me just highlight why I'm showing this. And the reason is that I only have the beta equations in this case. I do not have a spin chain. So we can only solve the spectral problem. I don't actually know what the underlying non-trivial matrices are, and so on. So it's a very interesting problem, I personally think, to understand some kind of spin chain picture in this regime. So if you're interested, I will be happy to discuss this further. So spin chains will allow me, in some ways, to get a good starting point on many problems. So I highlighted some of the things we have been able to do, but of course there's many things we cannot do, or things that are only partially completed. And so here are some typical examples. So it's 3-point functions, overlap, 1-point functions, which naturally will connect with the boundaries that I will talk about later. And then there is a huge problem, which is generalization beyond n equals to 4. So what does this mean? It means that you want to do exactly what I described before, but try to do it for spin chains with different symmetries than PSU 2,2/4. So in the language of rational spin chains, this would be trying to understand what happens beyond SUN. And generally, this is quite hard. At least it's very hard for me, since the Q systems and so on are much less understood. Of course, you can start from some kind of non-trivial matrix. It's more easier to understand how to generalize this for different symmetry groups. So this is kind of the idea, that I want to understand spin chains, and then I hope I get inspiration to go to some kind of QFT and learn things non-perturbatively in this regime. All right, so with that as motivation, let me kind of jump into actually doing spin chains. So I'll start with this kind of basic review of Q functions. And from the talks yesterday, of course, I'm very well aware that most people here know perfectly well how Q functions work. But let this serve as some kind of introduction to notation, and hopefully a different way of thinking about some very basic statements. So I'll start from the typical example of the XXX spin chain. So I have a spin chain, I have a lot of sites, and on each and every site I put a spin, and it can be either up or down. So we have at our disposal an R matrix. So the R matrix allows me to essentially scatter particles, and here I've written it down in some kind of approximate way up to some overall prefactor. And once I have my R matrix, or equally well my lax matrix, I can construct my transfer matrix. And the transfer matrix is, of course, simply me tracing out an auxiliary space and using my R matrix over and over again for each and every site that I have on my spin chain. Now, it's quite an amazing fact that all the eigenvalues of my spin chain take a very compact form. Unfortunately, here we have, of course, the first typo. Should be a minus sign here. That's quite embarrassing. Luckily, people here are well aware how these things work. And so this here is some way of writing my T function in terms of Q functions. And my Q function encodes my beta roots in the standard way. So what's an issue with this formula? Well, an issue in some sense is the fact that it's not explicitly polynomial, while the transfer matrix as I started with will be explicitly polynomial. Of course, the way to fix this is to impose beta equations. But if we were lazy, we would like to have a formula which we necessarily could use without imposing beta equations. So let me do that. So the way I do this is by introducing another Q function. So now I have Q1 and Q2. And now everything looks explicitly polynomial. So I have a formula now for the eigenvalues, which is simply this determinant of Q functions. Of course, since I have introduced another auxiliary variable, I have to somehow connect it to my previous one to make sure I reproduce the previous formula. And the way this is done is by simply imposing these QQ relations, or Wronskian relations, among Q1 and Q2. And so I force this QQ relation, setting Q1 and Q2 equals to U to the L. Now these formulas are useful because they're easy to generalize for transfer matrices for higher spin. So if you want to construct a transfer matrix with higher spin, what you do is you take fusion, right? Take two particles together. Luckily, the only thing that happens is that I get some additional shift in my first determinant formula. So a natural way of thinking about this is to think about the Hirota equations. And what are Hirota equations? Well, they are essentially no more than Plucker relations. So I have determinants, I use a Plucker relation, and I get my Hirota equations. And so this way is an effective way of parameterizing the solution to the Hirota equations. And essentially this here is quite independent of the model that I'm studying. So where is the actual information about the model? Well, I start out with a rational spin chain, right? And so where do I inject this information? Well, I inject information in the QQ relations. This is the only place I'm making an actual contact with the polynomiality of my initial transfer matrix. I, of course, also have to specify some analytic properties of my functions here. And we know, from a rational spinching point of view, that Q1, Q2 should be polynomial. But if I were inclined, I could try to change those analytic properties and find another model which this would reproduce a spectrum from. And essentially, this is the kind of philosophy when we do QSC. We start from formulas that don't make an explicit reference to any sort of analytic properties, and we try to generalize those. So the idea is to write down solutions to algebraic equations in a quite algebraic form. So to do SOV, I will have to generalize slightly and consider a more general setup. And I will do so basically in two different ways. The first way is to introduce inhomogeneities. So these are just numbers that I will attach to each and every site on my spin chain. I suppose that's the easiest way of saying it. So what do these guys do? Well, the only thing they do is that they modify my source term. And my source term is the only place that I'm telling you what the actual representation of the Yangian is that I'm studying. So the only thing that happens is that I get this u to the L, now becomes u to the minus theta I, and I have each and one for every site. And I will call this object q of theta. So this encodes all my inhoms. The second thing I will do is I will try to introduce twist. So the reason I'm introducing twist is to make sure that I have solutions to the beta equations, or rather the QQ relations, to each and every state in my Hilbert space. So if I did not introduce twist, I would have less solutions than the number of states in my Hilbert space, since some of the states. Yes, please. Oh, fantastic question. Thank you. Just a definition. Let's see here. I should have hidden it here. So that was hidden away here. So the only thing I mean with this notation is that if I have an n here, or a plus or a minus, if I write plus, I'm hiding +1, because it's a bit too much work to write 1. And all I do is that I shift my spectral parameter here. So all functions that only have this kind of superscript means that there are functions of the spectral parameter, but they are shifted. Thank you. Thank you for letting me clarify. So I twist in order to make sure that I have enough solutions to reach all states in my Hilbert space. Now, the twisting can be done in many kind of ways. I will pick this quite slightly awkward looking form of it, which we usually call companion twist, which turns out to be very, very useful when you do separation of variables. With that said, most formulas will actually not care about the particular form of the twist. This is just useful when you sit down and you do computer algebra to make sure that the equations you write down actually do match with some kind of operatorial construction. And then if I want to be a bit more serious about it, this is how you would have to program it into Mathematica with your lax matrices and your twist matrix. Yes, please. I do not know. I don't need it. I could have equally well twisted with the diagonal one. The main benefit of this is that it will make all my my SOV bases twist independent later. But this of course has the same eigenvalue as the typical just diagonal lambda 1 over lambda 1. Absolutely. Yeah. I mean, I could have tried to do the 1-1 as well. That would, I mean, the just diagonal twist would have been perfectly fine as an option as well. None of the formulas really changes. So the only thing that happens is that your Q function here will pick up this twist. It doesn't really care about the explicit form of that thing. The eigenvalues will work out anyways. Mm-hmm. Yeah, exactly. That's the idea. Perfect. Yes. Yeah, that's a great comment. So the idea here is, of course, that this twist will act on my majority matrix and make sure that I get an operator when I do my SOV, which will actually have a good spectrum. I will try to kind of avoid even this language and do it even more functional. But that's, of course, the underlying motivation, and that's the reason that Paul and I think Dima tried to propose this, at least for the GLN case. It's a great way of picking your twist. So what I did before was for the SU2 case. So let me generalize for the SUN case. So I won't go too far into SUN, but at some point I would like to consider SU3 as kind of a non-trivial example of what I'm doing. Because the truth is that functional SUV, of course, comes to its full power when I consider higher rank. If I stay within SU2, it's quite possible to work out everything with standard operatorial methods. But for SU3 and so on, it gets more difficult, at least for me personally. So let me show you how I do SUN-Q systems. So I have this way of thinking about it, where I take a Q function and I attach a Q vector to each and every node on the Dynkin diagram. So this A here will run through the fundamental representation. So A3, one of the real forms of A3 is SU4. And because it's SU4, that A will run from 1 to 4 in this particular example. If I were to go to SUN, it would run A from 1 to n. And then on each and every node, I have an antisymmetric guy. So how do I define these antisymmetric guys? Well, they're defined through QQ relations. So this here is the equation that I use to define the higher Q functions. And in principle, this would allow you to solve for Q2, Q3 in terms of Q1s. And if this is convenient or not depends on the problem you're trying to solve. And then at some point, I also have to inject some information about what kind of actual physical model I'm looking at. And in this case, I should take my Q of 1, 2, all the way to n, and put it equal to Q theta. And I will also take, if there's no index here, equal to 1. So if you were to take this and plug it in for SU2, you would recover the standard formula I showed before. And so for SUN, there is also a T system. And the idea is that I can once again solve my T system using determinants of Q functions. So here I have tried to draw the case of SU3. And I have this lattice where I define my Hirota equation. So the Hirota equation, as written here, is essentially the same as for SU2, but I have to include some additional indices due to the possibility of doing antisymmetrization. And the formula for my T functions is once again some big determinants. And it's easily written down with some just shift of the spectral parameter. And then T2 will have a very similar form with a slight modification of the shift. And the idea is once again that when you have this form, you take it, you plug it into this equation, and it's an automatic solution. Right. So from this kind of construction of my T function, I can derive a functional relation, which is called the Baxter equation. So the Baxter equation here, I wrote it down for SU2, the first equation. And I've also introduced a shift operator, which has as its life job to shift by spectral parameter. And so the first equation here is, of course, nothing else than the definition of the transfer matrix I defined on almost the first slide. Now, the power of this kind of determinant form of Q functions is that you can find a similar functional equation also for higher rank algebras. So it is a consequence immediately of the fact that I can write my fundamental transfer matrices as determinant of Q functions that I have a Baxter equation for any kind of rank. So for example, I've written it down here for SU3. So I have some additional shifts, and I have some T functions now, both T11, T21. How do I derive such an equation? Well, you just start from a trivial determinant, you expand it out, and you identify the minors with transfer matrices. So from this point of view, the Baxter equation is completely trivial. When is it not trivial? Well, it's not trivial if I were to instead just start from the Baxter and feed you the value of my T functions. Of course, if I have Q, I can reconstruct T, and this tells you how to reconstruct Q if given T. And so for notation-wise, I will write this as some kind of operatorial equation. So I have the Baxter operator acting on Q equals to 0. And this here is kind of the main functional equation that I will use to do separation of variables. Right. So here is some more speculative stuff, but since there's a lot of experts. So of course, something that I find a bit unsatisfactory is the fact that I presented SUN. But if life was good, you should be able to do this for any kind of algebra with ease. And so when it comes to Q systems, what people have been trying to do mostly is to study SO2n instead of SUN. Now, SO2n has an issue with the story that I just presented, and the issue is that there is really no good Baxter equation. So there's no as easy formula as I showed before. There's some infinite versions of it. Those become unhandy. But luckily, if you look in the literature, there is cases where there is a good Baxter equation. So for example, we can look at SO5 or SP4. So I just very briefly sketched how SO4 works. You have a vector representation, you have a spin representation, you have a bunch of R matrices, and you construct your T functions in a very similar way. And just to flash some formulas. So it was worked out by Kuniba and other people. Unfortunately, that citation seems to have vanished. That's bad. So there is a Baxter equation. It looks quite nasty. You can find solutions to it in terms of some generalized version of Q functions. They introduce some kind of crazy twist. But then you find solutions. And one can once again reconstruct all these T functions from Q functions. So this is at least like a nice case where one can try to do the functional SOV story again. At least hopefully. So this has not been worked out fully. I'm going to present some kind of conjectural L=1 equation. And then if someone else has tried to do this, it'll be very interesting to hear what you have managed to do. Right, so let me actually jump into separation of variables. So this here was just the part about Q functions. And so what I will mainly discuss now is the basic facts of how to do separation of variables for functional SOV. And so there's, of course, quite a few experts in the room who hopefully can fill out any kind of details if I'm missing something. So let's see what we can do with SOV. So before we discussed computing the spectrum. And now we're going to try to compute scalar products instead. And so let's look at the basic idea. We have some transfer matrix. We act on some eigenstate. It gives us our eigenvalue of our transfer matrix. And then the immediate consequence here is that if I have left eigenstate, right eigenstate, they should be orthogonal to each other. What do I want to do? What's the goal of this entire part? The goal of this entire part is to try to reproduce this kind of Kronecker delta as some kind of equation for Q functions, and then extend this and hope that it also gets the proper normalization correctly, which it, of course, will happily do. So let's just take a look at the reconstruction of this delta function in terms of Q functions. So the idea here is to look at the conserved charged. So I will take my transfer matrix, I'll expand it. So it's some polynomial. The first coefficient of that polynomial is actually independent of the state. So if you twist your spin chain, it's going to be some character. While the rest of the coefficients are non-trivial functions, your equations, your integrals of motion. And I will look at not quite integral of motion, but rather the difference between two integrals of motion. And I will try to write down an equation on these guys. And I want to see when this equation can be equal to 0. Because when that equation is equal to 0, of course, that implies that state A and the state B must be the same state. All right, so the next step here is basically a almost trivial identification of the Baxter equation I wrote down before for SU2. This guy here will contain exactly the integrals A, this one will contain the integral B, and then there will be some additional shifts, but all those shifts are state independent, so they have to cancel in this combination. So what I will do is I will keep working like this. I can, of course, multiply both sides on the left with an arbitrary Q function once again. And then I will try to take an inner product of this equation. And I'm taking this inner product by introducing this bracket. And the idea is that I introduce a bracket such that it's equal to 0 on the right-hand side. So how do I make it equal to 0 on the right-hand side? Well, I use the fact that this is a Baxter equation. Or this is a difference between two Baxter operators. So the idea is that I want to construct a bracket in such a way that I can flip f and g, with O being an operator that acts upon them. If I can do this, the right-hand side would automatically be 0, because, okay, I can hit with B first in this particular case. I can swap these two guys around and then just act again equal to 0. So the goal is to construct this bracket with these properties. So how do I actually do this? Well, if I just brute force look at what the expressions are that have been written down, you can easily see that it's quite manageable by simply evaluating it at a specific point. And that specific point is, of course, fixed by my homogeneities. So I will evaluate a function f inside of my bracket at theta of alpha plus I and theta of alpha minus I. And then I'll add some prefactors to take care of the fact that there's some source term in my Baxter equation. So this here is the identity that I would like to prove. What I'm trying to state here is that if I use my answer, what happens on the left-hand side is I get this particular combination. What's the point of this combination? Well, the point is that I can flip f and g. You cannot see any difference. It's symmetric under that, which automatically implies that this equation has to be true upstairs. So, great. Of course, I only give you one solution, but that will be quite enough for a particular needs. So the idea is that I get this set of equations. And of course, if we have a non-trivial equation with some matrix multiplying it, and it's equal to 0, then the determinant of that matrix has to be equal to 0. So I consider simply the equation of taking the determinants of all of these coefficients. And that gives me a proposal for what the scalar product should be. So the property of the scalar product is that it's equal to 0 automatically if A is not equal to B. And if A is equal to B, this here will not be equal to 0. And I introduce some normalization to take into account that I have to match against the previous formulas of, say, some operatorial work later. So this normalization here can, of course, be fixed, and it was fixed by people when they did this to make sure it matches with the expectation. Yes. Let's see. You could potentially have a null state, but as long as I think you properly twist and so on, since I will have that as a parameter in there, I suppose that should keep me relatively safe. So maybe if I go to some special value of my in-homes and I turn off everything, I guess I can get some bad cases. But if I keep everything arbitrary, I should be able to get at least 1 point where it's nothing. I will be admitted that on Mathematica, it's not 0. Of course, also we will see it is not 0 by expanding it out later and making sure. Here I've also written down another way of saying this. So before I just took my bracket and evaluated it at some good points. Another way of evaluating functions at good points is to do residue calculus. So I've written it down here as some kind of residue calculus expression. So this is just an integral over a great enough circle to make sure I encompasses all poles. This here is a measure, and this is the function at hand. And that measure, it looks quite nasty, but it's really not. So the only thing it does is that it introduces poles at exactly these points I was evaluating at before. And this guy here is simply some periodic function which induces additional zeros. And of course, maybe I should have emphasized this more. I can of course take this at different values of my inhomogeneities, which makes sure I do get a determinant of the correct size. So here is an actually explicit example if the formulas were looking incomprehensible. So here I just wrote out what it is for SU2, L equals to 2. And usually it's also a natural question to ask, what does these Q function look like? So I wrote down what they look like. And you can see that the first one looks great. It's just a twist. The other ones look absolutely awful in every kind of way. And they are, unfortunately, not that easy to work with in general. But there's a trick in life, which is that if you believe your equation is correct, you can check it for many, many points, which means that I can plug in numerical values for this, and then it's very easy to do everything. But keeping all of these inhomogeneities explicitly, it's still quite a challenging task. And of course, nothing you actually want to do. You want to keep everything explicit and implicit, and make sure that you get nice functional equations without having to worry about the exact form of these objects. And then just a quick word on actual separation of variables. So the idea here is that if you write out the function that I gave you, what you're going to find is your Q function evaluated at specific points. So I evaluate at this theta of alpha plus minus I over 2. Okay, so where would this come from? Well, this would come from essentially some inner product between this state x with my eigenvector, and this will simply become a product of Q functions. So in this language, what happens is that the inner product becomes this simple sum over these wave functions with some measure in between. And this was worked out explicitly what it is by Federer or by Paul. And it can be computed through some process you refer to as signification, which is completely explicit, but in honesty also quite messy, which is the reason that the determinant formulas are nice. Yes? Well, a signification is just a way of correctly distributing all the values of I here. Why sigma? Well, sigma usually denotes permutation. So it's just a way of permuting the different objects to make sure you get all the things in the correct sum. We can find the explicit expressions later if you want to. Another way of thinking about this x is that it's an eigenvector of this B operator, or this B good operator. In that case, the B operator simply encodes the spectrum. It also allows you to build the eigenvectors by repeatedly acting with B on your vacuum. So this would be how to approach this from a kind of operatorial point of view instead. But if you do the functional way outlined above, of course you essentially don't need anything of this unless you want to make, well, explicit comparison to the other formulas. So for higher rank, what happens is that things stay essentially the same. So let me just briefly outline what the differences are. So for SU3, we have more transfer matrices. And we also have more Q functions, as I showed before. So here I will use this notation with Q1, Q2, Q3, and then I will also consider the functions with the index upstairs. And this gives me some Q function, which relates to this with two indices. What happens is that the Baxter equation now has to act both on the Q function with upper index and lower indices. But once you have this, you repeat the same kind of trick. You find yourself that the scalar product takes once again the determinant form. Main difference being that the Q functions now appear with one with up index and one with down index. And there's some additional shifts in the game. And there's additional shifts in the game because the Baxter equation now has additional shifts sitting at each and every transfer matrix. So for SO5, one can try to do exactly the same. For the length 1 case, for example, this is what the determinant will look like. And this is some kind of measure that you will have to compute. And so if anyone wants to check this from functional, this would be great to see if this can work.
From operatorial.
Oh, yes, sorry. Thank you. Well, I mean, if you want to double check my work from functional as well, I wouldn't mind. So both are a good exercise. Okay, so Baxter equation for SUN can be used to find scalar products. The resulting expression is some kind of a determinant. And of course, it would be interesting to work it out for other cases. But in the meantime, the few minutes I have left, let's just do boundary overlaps. So for boundary overlaps, what you do is that you want to consider scalar products not between two eigenvectors of the transfer matrix, but between an eigenvector of the transfer matrix and what's known as a boundary state, or the integrable boundary state. And the definition of these integrable boundary states is that they annihilate the odd charges. So our goal is to compute this overlap, but I will do it for higher rank cases. Now, the way we do this is that we simply start from some slightly generalized equations for SU3. So we have two transfer matrices. They have to satisfy this kind of inversion relations. To make sure that I have states that allows for this, I consider a spin chain. And the spin chain will have sites both in the fundamental and in the anti-fundamental representation. And I will tune my inhomogeneities to make sure that states like this exist. Which means that I will take them to be equal to theta on the fundamental and minus theta on the anti-fundamental. Then you follow the standard procedure, you write down a Baxter equation.
Why do you take this particular thing where you have fundamental and anti-fundamental? Could you just take a standard extension?
I think in general, I'm not sure that there's going to exist any good W in that case. Basically, yeah, please.
At least in that case, you have the full equation operator.
Yeah.
Yeah, and fundamentally, you keep the two.
Well, yes.
But it's only different. So I was wondering about the same question. But it's actually key with paper use setback to make this partition function less true.
I mean, if you have fundamental and anti-fundamental, you will have singlets automatically. That's kind of the helpful part about it. I mean, when you have an anti-fundamental and a fundamental, they automatically have some good singlets when you take tensor products, and that's basically the idea that allows you to fix this W. Because when I go to the next slide, what I do is I fix W more precisely.
You need to fix the homogeneity to have this good singlet.
Yeah, sure. That's the reason.
Yeah, and also if you want to work with homogeneous chain, then you have to modify the integrability condition.
Yep.
You have to change the transfer matrix in the right hand side to the anti-fundamental representation.
Yeah, that's true. Right, so, well, simplest case is simplest, right? So that's a good thing to do. So this is just fixing the W a bit better using K2 relations. So to actually get a unique state. Otherwise there will be many states that would satisfy these kind of conditions. And then you have basically QQ relations once again. And the QQ relations are such that when I pick exactly the properties that I mentioned before, I can automatically get a solution by flipping the sign of U, which means that I can easily map two different solutions to each other. And this will also mean that for each and every integral of motion, for some state A, I'm going to have another state where I just flip the sign of the odd charges. So what I do is I write down a Baxter equation. So it's the same procedure as before. But now I consider not quite A and B, but I consider state A with A dagger. And when you work this out, you get an equation for only your odd charges. And it becomes this. And once again, this gives you a proposal for the overlap. You would also find exactly this kind of formula if you just worked out a scalar product between A and the parity inversion of A, which takes this kind of diagonal form. And here there are two different determinants. So the point is that this here singles out the correct one to study if you want to study the overlap with boundary states. And for example, if you take these formulas, you can compute some normalization independent object, which gives you this typical determinant plus over determinant minus equation with some overall normalization. And in principle, one would like to do more. So try to actually compute more than just the scalar products, but also compute some kind of operator insertions. And luckily, this can be done. And it can be done using some sort of principal operators in terms of some other function. But I will leave this to Paul, essentially. So let me move to conclusions, because I think I'm essentially out of time. So the idea is the function SOV allows us to compute a lot of different things. For example, scalar products and boundary overlaps. The hope is that when you do a functional approach, you can more easily generalize to higher rank, where methods, usually algebraic, will become more and more cumbersome for each and every rank you add. Also, for me personally, of course, within ADS CFT, essentially I need to do every functional, because I don't know what an operatorial description would be beyond one loop. And then, as I pointed out, as far as I'm aware, like extending SOV to other algebras is still difficult in general. And perhaps the most important thing for me personally would be to try to do this for supersymmetric spin chains, which seems to be quite challenging in general. Okay, thank you so much.
Okay, any question? That's your comment during your talk. We have technical question to reconstruct. When you have all this Q, Q1 to 3, for example, for SL3, and you can after rewrite everything just in terms of 2. With you have this rational polynomial way to write, and you have this way you can have better equation, and you have this ratio rational function.
Yes.
And there's a nice, easy procedure to move from one to the other. For example, if you have an inhomogeneous TQ equation at a certain point and you want to avoid everything, and you have the Wronskian, we look about eigenvalue, and the structure is different for modified better ansatz. So it's something I try to understand. In particular, if this picture is connected only with homogeneous TQ equation, just without this correction proposed by the Chinese group. And this is not clear for me, so maybe you have some idea. Or
Well,
you know.
I can only say what I discussed briefly yesterday with Paul and other. So the way I presented this, I will not have this in a homogeneous piece. I will always have a homogeneous equation. But then again, I can always try to redefine my Q function to create some kind of inhomogeneous piece.
Okay, maybe in other words. So if you take SL2,
Yeah.
generic boundary,
Mm-hmm.
with SOV, you can construct this 2Q operator.
Yes.
You did it. It works, and after you can rebuild of two kind of TQ equation. Homogeneous. No, you only one type.
I can only read off one type.
Yeah.
I don't know how to do the inhomogeneous case.
But for XXX periodic with the anti-toroidal case, you have two possibility. You can have usual and unusual. But the point is, it seems for me, what I observed, that this Bromskian relation is not the same for this other picture. So I was wondering about the generic SL2 XXX model with two generic boundary.
Okay, so
There's only, but there's the procedure is what was done by Leon's group, maybe in some paper. But this the method to move from one to the other is the same each time.
I don't know. I have never tried to do it.
I will ask.
But we can try.
Okay.
I mean, the only hope I have is that I redefine the Q functions with some prefactors, and they should give the homogeneous pieces. If I can't do this, I suppose I will have to actually come up with something new, which would be more fun. It's
Okay. Thanks.
You have a homogeneous space. I think that the problem is proposed by the different group, also recommended and so on by the seminar yesterday, is that you have an inhomogeneous piece, and the difficulty is to find a solution of this new form of Baxter equation. This is, I think, the problem. And then it's not obvious to reproduce that homogeneous piece. I'm not saying that you cannot. Maybe you can, but this is the order of the problem Yes, but I'm really not an expert about the field, but I think that technology can be extended as far as, but I have understood just a little. And yeah, basically okay, I don't want to, we can discuss privately better.
sure.
Okay, any remarks or Christian?
So very nice work. And my question is that the overlap between two eigenfunctions, one is on-shear or all of the off-shear. So because the Q function usually depends the solution of the beta-Lorentz equation. If you're on-shear, that means the rows of Q function should satisfy some beta-Lorentz equation. If the off-shear, that is arbitrary Q. So all of your overlap is on-shear, or one is on-shear, another is off-shear.
So in this approach, they will all will be on shell in the idea that they will all satisfy QQ relations, which will imply beta equations, which will fix all parts. So they're completely fixed.
And the Bromskian fix exactly the zero of the Q. You know the additional solution. More efficient.
So for all the system with the algebra, like the other than the A type, usually for the other type should have some, for the base state, you should have some tensor structure, not like the A type. A type just some big action on some reference state.
Yeah.
But for the other algebra, rather than the A type, you usually should from some kind of structure like the tensor case. Not will.
So you mean this kind of method vector, or we have different type of operator?
Yeah, it's two particle 3 particle, then very complicated.
And this first question about the be good if there's only one type of particle, the first one you publish, or if you have a more generic representation, in particular the one with this fundamental, the be good is the structure is more complex.
No, it will just not to work, nothing. So it will separate variables, but it will not create eigenstates.
Okay.
So the case when it works is when there is only one non-trivial weight in the representation. Then you can generate states like BPP, and even though in principle there are several layers of data roots, only one of them is actually needed.
Okay, so what you say is...
But for a general representation, even for A series, it will not work. At least, well, maybe there is some very fancy way to make it work, but we don't know. Maybe Simon has something.
No, I wish I had some more input, but no, I don't know anything more than exactly what you said.
But functional does work. The scale point still works on your representation.
Yeah, that's true. Yeah, I mean, we can construct functional for the boundary. Of course, we have two different representations. We have the fundamental and we have the anti-fundamental. We can of course still do this, so this works, as Paul said, but we don't exactly. But we don't have a good B operator. But that doesn't prevent me from constructing all these states, anyways. So, but I would love to have a good B operator. That's okay.
There's a point to have some states labeled by beta roots.
Yeah.
But in some case, if you have labeled by Q, you have the beta roots inside.
Exactly. Yeah.
And it was the question, and the point is about the beta equation are replaced by the Boris scheme. Like you I thought you have this product equation. And they're not equation to fix all the equation, at least numerically. And even it's cool, and it was said too by, don't remember the guy that did that.
Yes, so proof
For example, he find a proof recently that shows that the homogeneous limit. It's good. Okay, any more questions? Okay, so maybe you can, when you want.